This is not working by the way. So
It's not working? Okay.
don't
Am I wearing it?
yeah, if you want, yeah. At least you would have the
Microphone, yes. Okay.
good morning.
Well, thanks very much to all the organizers for putting this together and inviting me, and thanks for coming when you could be having your breakfast right now, but or sleeping still. So let me get started. So I'm Mikael Rechtsman from Penn State, and I'll tell you about quantized nonlinear thallus pumping. So these are my group members, Hung Bin and Little John. We have a big John up there in the middle, and there's also a little John, is another guy. But Little John is much, much bigger than the big John, actually. And Marius Jorgensen has actually now moved on to a postdoc with John Simon at Stanford. Yeah, we've got a number of students and postdocs, and I'm actually hiring right now. I was accosting some of you to see if you have any group members that might be interested. I'm hiring postdocs and students, so if anyone is interested, please feel free to get in touch. All right, here we go. So we're going to start with the integer case, and then later on, I'll move to the fractional case, and I'll keep that as a little surprise. So I think many of you know what the quantum Hall effect is, but I'll do a quick summary anyway, a very, very brief version of it. So what is the quantum Hall? You have a two-dimensional electron gas, so electrons will be moving the plane, and then there's a magnetic field, which is perpendicular to the plane, and then you measure the transverse conductance. You put voltage in the x direction and measure the current in the y direction, and those two give you a conductance. And that conductance is sharply quantized in the quantum Hall effect. So it's equal to a fundamental constant of nature, e squared over h, times an integer. And that integer is a topological numerical constitution. And the point that this integer is a really important one. What it means is that you can add disorder to the system, any kind of efficiency. And because an integer cannot go smoothly to another integer, take one gradually to two, the quantized Hall conductance doesn't change. And that means that you can measure this quantity. You have precision these days of hardness. It's really remarkable for so it's really a beautiful physics. It's, you know, played a part in now, I would say, 3 Nobel Prizes. It's absolutely wonderful. We have reinvented it in different ways over the years because it's such beautiful physics. We've seen different versions of it, and I'm going to be telling you about another version of it, but this time in a very different context than we're normally used to, based on the picture I just gave. The quantization is normally explained by one of two mechanisms. One is the edge explanation in terms of edge states that don't scatter, and another is in terms of the bulk, and I'm going to be focusing on the bulk. Okay, and that's where thallus pumps come in. Thallus pumps were originally proposed by Thallus around the time that the quantum Hall effect was introduced. It turned out to be completely equivalent to the quantum Hall effect, integer quantum Hall effect mathematically. Let me tell you what they are. So the analogy here is this Archimedes screw pump. Right, quantum Hall effect, as I described, is a two-dimensional system. This is a one-dimensional system, right? The screw pump here, it's 1D, and it's periodic, but it's also periodic in time, right? And we treat it as being adiabatic. So as you turn the crank here of the thallus pump, then you're bringing a fixed number of water molecules up from the river to the bank. And it turns out that mechanism of taking a quote unquote quantized number of water molecules, this water molecules are discrete objects. This mathematically, if you put it in terms of wave mechanics, in terms of the Schrödinger equation, is completely equivalent to the two-dimensional physics. So you're basically showing here that 1 + 1 is indeed equal to 2. But it's sort of a different way of looking at the quantization mechanism of the quantum Hall effect, making that link. I think I would be a little over time, so I'm not going to go into all the details. You can ask me about it. But essentially, you're inheriting the same physics, and that's what they realized very shortly afterwards in the early 1980s. The key point here is that you have to have filled bands for this to work, and this is what Thales showed. He assumed very reasonably that a 1 + 1 mesh model with the Fermi level completely filled bands. And if that's the case, that's the condition, then you get this quantization of pumping of charge. Another manifestation of that is through the Wannier functions. So Wannier functions are functions which can be localized, which are not eigenstates in the system, but they are composed of equal populations of every state in a given unit. So with some n, you take equal population of all the states, and you construct this function, which can be localized, and then you can track its motion through the pump. And if you do that, what you find is that its center of mass moves over. So you can see this is time and this is space. So it moves over, in this case to the right, by 1 unit cell. And that corresponds to having Chern number 1. So the amount that the Wannier function moves over is equal to this topological invariant, the Chern number. And this is something that we can do with bosons. Of course, with bosons, we cannot populate out to a Fermi level, just fill bands, that's not exclusion. But we can construct a Wannier function and let it propagate and see what happens to it. So this is a way that we can actually measure quantization without having a Fermi level. It's very analogous to having a Fermi level. What we've been interested in is the nonlinear domain. Okay, so with fermions, of course, there's exclusion, so you can have only one particle per state, but that's not true of bosons. You can fill it up. And so we want to ask a kind of unconventional question. What happens when you combine these topological effects with bosonic? In the past, we've done a number of experiments on linear dynamics where we are effectively, when it's non-interacting, you have sort of the same physics as in the electron case, give or take a few things. But here we're asking a question that really has no correspondence in the fermionic case because of this nonlinear term. So this is basically a Bose-Hubbard type Hamiltonian in the mean field limit, so Gross-Batyevsky, but where this Hamiltonian will have some topological structure. It has something interesting about it going on. And so we call this topological nonlinear optics. Something very different than you would have in the fermionic case. So to explain some of our experimental results, I first have to tell you about solitons because it's something that we see very naturally in our experiments. They come up all the time. Solitons are wave packets that, by virtue of the nonlinearity present, they induce a potential for themselves, for which they are themselves constants. And so, in other words, you have some wave packet. The wave packet produces a potential. You can see that this is a potential term. It's just, in this case, psi squared. So now you have this potential well, which is psi squared. You calculate the bound states of that potential well. You see it's negative, so it's going to be negative. It's going to have a bound state. Then that eigenstate, that first eigenstate, for example, that you get, is actually that original potential that you used in the case of a soliton. So it's this sort of self-consistent loop that gives you the soliton. Okay, these are, in some sense, the fundamental units of many different PDEs. If we think of plane waves as being sort of the fundamental unit of wave equations, solitons are kind of the fundamental unit of some nonlinear wave equations. So here you can just see what they look like. So here they were first discovered in water waves. You can see here, this is sort of a wave packet that just keeps propagating. It's balancing the dispersion and the nonlinearity. So instead of dispersing, it just sort of keeps going forever like that. Here's you can think of this as a laser beam. So normal laser beam diffracts, right? So if you If you take a laser beam and you make the aperture really small, then it's going to spread out as a function of distance from the aperture. But if you have enough nonlinearity, then you create that potential well for itself, and you're creating its own waveguide. It's making a fiber for itself. And to show that these things sort of pop up spontaneously everywhere, this is a simulation of modulation instability where you start just with a plane wave. And as long as you have these attractive interactions that I mentioned earlier, that I showed in the equation, if you just put a little bit of noise, then you have some instability. The wave packet falls apart, and what forms? Solitons, spontaneously. They just come out. So in some sense, in our experiments, we could launch in whatever we want, and eventually, if we could wait long enough, we would see solitons. Okay? They come up absolutely everywhere. We see them in polymer chains, so that's the SSH model, ultra cold atoms, in MEMS devices, they're really being used for technology in Kari Vahala's group and Tobias Kippenberg's group for generating optical frequency combs and doing mode locking and so on. So it's really ubiquitous in physics. So the system that we use are laser-written waveguides. So I'm an experimentalist. Let me tell you about the experiments that we do. To fabricate these waveguides, what we do is you bring in a laser beam and it focuses into a piece of glass, high quality, what's called Eagle XG borosilicate glass. And locally, you ablate the glass at a tiny spot. And what that does is to increase the refractive index by a little bit. So you just increase that refractive index by 10 to the minus 3. And then you can drag the glass along, and that creates a whole waveguide because it's like a region of higher refractive index. The parameters are very similar to an optical fiber. And here we just sort of check that you have evanescent coupling between two waveguides. So if you put two waveguides close to one another, then there can be evanescent overlap, just like put two atoms next to one another, or you have two potential wells next to one another in an ultra-cold atoms experiment, or whatever. You have hopping between them, and the hopping is evanescent, as we can see is in this plot of hopping versus the distance between the waveguides. So if you write a whole lattice of them, now we have this artificial two-dimensional material. So here's an animation of the waveguides being written. You can see there's this lens that's being focused down onto this piece of glass there. And this is real time, so it takes a few seconds per waveguide. And so if we create a device with hundreds of waveguides, then it might be 10, 20 minutes or up to an hour if it's big. The diffraction of light through these waveguides is actually governed by the Schrödinger equation. And if the power is high enough, then it's the nonlinear equation, because this refractive index here, which is acting like a potential, has some nonlinear response to it. So you increase the beam and you get exactly the Gross-Kotelski equation, the time-dependent Gross-Kotelski equation. Okay, so what we do is we write Thales pumps. We laser write Thales pumps. So we come up, starting with this model, it's an AAH model inspired by Oded's original paper on Thales pumps and optics. So we've got this three-site model. We calculate the band structure. The bands have Chern numbers -1, +2, and -1. There's 3 bands because there's 3 members of the unit cell. And then we actually laser inscribe these things. We actually make them. And here's a sort of a picture of what they're doing. Remember, I told you that the Thales pump is a 1 + 1 dimensional system. So the 2 dimensions here are the x direction here. So we have sort of discrete sites. And the z direction, which acts like a temporal coordinate. So z actually is just like t in the Schrödinger equation here. So we're looking at diffraction instead of looking at time evolution. And then here's just a picture, a white light picture of these waveguides. And you can see in space, there's 3 members of the unit cell, and it's just being modulated. And so if we were to populate a Wannier function, one of these bands, say the Chern number -1, then what we'd expect is, as we watch that Wannier function move, we expect it to move over to the left by 1 unit cell, precisely 1 unit cell. We can get an exact Wannier function. It moves over by that amount. Okay. I'll spare you some of the experimental details, but basically the summary of this slide is that we're using this very, very weakly nonlinear glass. So we really have to blast the hell out of this thing to get any form of nonlinearity, which means that we can't use CW light. We have to use pulse light. And that presents its own problem because there might be dispersion, there's self-phase modulation, there's all sorts of other stuff that happens with pulses that we don't want. So we just go through all these checks to make sure that, you know, if we claim that we have the nonlinear Schrodinger equation, we really do have the nonlinear Schrodinger equation. And there's a whole rigmarole that you can, if you happen to be interested, you can ask me about. The biggest problem is self-phase modulation, where you have some pulse. And by putting a pulse through a piece of glass, you chirp the pulse through self-phase modulation, that broadens the spectrum. Then you have this huge spectrum, the hopping is a function of wavelength, then you don't have a well-defined hopping, and it's a big zoo. So we have to do a whole bunch of tricks. As always with experiments, the most time is spent on stuff that no one cares about in a talk. So this took us a while to figure out. Anyway, so let's talk about what happens. So let's say that we put in a Wannier function. So you're looking at evolution in the downward direction. So you start here with a localized Wannier function. As I said, Wannier function is not an eigenstate, it's a localized state. So we expect it to spread out as a function of position and as a function of z, propagation along the axis. And that's what it does. It spreads out, but it also moves over to the left in this case, because it's a Wannier function of the first band with turn -1. On average, its center of mass moves over by 1 unit cell to the left. It's a bit hard to see there, but I have a plot showing the center of mass. But then something funny happens. We turn up the power. We look at solitons. These are not quantum. And what we see is that the soliton is sharply quantized to 1. To the turn. And that was a surprise to us, because if we look at the projection of the soliton onto the stated band, it's not equally populated. So this is very different than equally filling every member of the band. And so, and we checked, maybe it's almost quantized, you know, maybe it's off by a part thousands of points in it or something. But the answer is no, it is rigorously, sharply quantized without being a Wannier function. If we turn the power off, or we take it towards 0, so we can still see a signal, but there's no nonlinearity. For the weak nonlinear regime, it is not quantized. So we see it spread out, and you lose the quantization. You need the nonlinearity for the quantization. So that was sort of the first surprise. But then what we saw is, okay, you turn up the power, and now something that's sort of obvious happens, which is you use so much power, it's strongly localized. It's localized into one side, and then it's just fully, completely self. And then it doesn't move, and that's obvious. But then the question is, how do you go smoothly from -1 to 0? It happens at a discrete power at which we have this transition. And I will show you how that happens. It's through a nonlinear bifurcation. And so here you see the motion of the thing. You have this pumping where you go exactly 1 unit cell, so 3 sites per 1 cycle of the pump to the left. Whereas here, for sufficiently high power, you have self-trapping. So in both cases, it's quantized. But in one case to -1, and in the higher power case to 0. Okay, so this is how it works. So here's the trajectory of the soliton. So it starts on site A, and you can see it moves over to the left to site A, but on the leftward unit cell. What these are bifurcation diagrams showing more modes that appear as you increase the nonlinearity, right? So let me show you what happens as we increase the power. So power is increasing, and watch what happens. New modes appear in the trajectory. Now you still have this path that's going along. It's unobstructed for now, but then at a particular power, the path bifurcates, And you can see now you're going from A to the same A. So that's how quantization is preserved in these nonlinear dynamical systems. It's through nonlinear bifurcations. So in electronic systems, quantization is preserved maybe by crossing the lambda level. You have a transition from one to the other phase, churn one to churn two, say. In these nonlinear systems, the way the quote unquote topological phase transition happens is through this nonlinear bifurcation. Very different mechanism. Very, very different mechanism than in the electronic case. And you absolutely need to have more than one, particle per state to be able to realize this distance. But it's still sharply quantized. So here's the experimental results. In this case, we pump by a third of a period, 2/3 of a period, and then a full period, just to see how this works. So here, what you're seeing is at low power, you just get a bunch of diffraction. We inject into this waveguide with the white circle, and then we get diffraction. And then for critical power, we see the state becomes highly localized and moves over to the left by one site. I have 5 minutes. You have to be no. I started maybe 10 after or something. Yeah. Okay, come on. But we haven't hit the good stuff yet. Okay, this is preamble for the later good stuff.
I think your mouse is not showing on the.
It's not showing on the thing. Oh, it's because I'm okay, I'll describe it more. I'm sharing the other screen. That's the problem. Then here, as it happens here, it gets self-trapped and moves over by 2 sites because this is 2/3 of the pump. And then finally it gets self-trapped. And here it moves over by 3 sites and gets more or less self-trapped here to the site in which you inject. So the experiments really show this behavior of quantized motion of the soliton. And we can see that when we plot center of mass also. Here's some numerics really illustrating the point that for each band, we're getting the behavior that we predict. So here's the soliton, and it moves over to the left by 1. That's the soliton for the top band. And then we take the soliton bifurcates from the middle band, and it moves over to the right by 2. This is the population. And you can see the population is fluctuating all over the place. There's nothing universal about it. Whereas the Wannian function population here is even the whole way through. So it's a Wannian function the whole way. So it is sort of funny that the soliton preserves this quantization. And then here you can see the different soliton it's moving over again to the left, corresponding to the turn number -1. Here you can see the transition happen. So there again is the soliton path. And now I'm going to vary some linear parameters. So I change the Hamiltonian a little bit so that I undergo a topological phase transition. Now look what happens with these bands. Okay, the bands are getting closer together, and then as soon as there's a band touching, so a topological transition of bands, we get this nonlinear bifurcation, which makes the soliton go instead of 1 to the left, 2 to the right, because it goes to churn 2. Right. So let's show that again, because my mouse isn't showing up. So there, on the right, the linear bands are touching. And as soon as they touch, watch what happens to the soliton trajectory and then the soliton wave function. So right now. So this is how you go, not smoothly from one phase to the other. Now, why is this happening? Why are solitons quantized? Their motion. The answer is, in a way, obvious in retrospect, which is that if you believe in adiabaticity in nonlinear systems, which has been established to some extent, well, you have to follow a ground state, right? Soliton is like a ground state. And so what happens is you go through a cycle of the pump, and you come back to the same Hamiltonian at the end of the period, right? So through one cycle in Z, one period of time. And you have the same Hamiltonian. And so you have to come back to itself, but modulo a unit cell. So it could have moved over, right? And in this case, it does, but it has to come back to the same wave function. So that explains integer quantization. It doesn't explain why it's the churn number. And we've seen that for low powers, it is the churn number, and then for higher powers, it's not necessarily. So at low power, we have a proof in this paper there's a similar paper by Nathan Goldman, similar result, I should say, proving the same thing at the same time, that you have this quantization at low powers, and you expand in terms of 1A functions, whatever. Okay. Okay, now the fractional case. I should say this is all really work of my student Marius Jurgensen and my postdoc Seba Mukherjee. Seba is now faculty at IISc in Bangalore, and as I said, Marius is with John Simon. Okay, here we go. So now the fractional case. So now we go from a 3-band model to a 5-band model. 5-band Aubrey-Andre. Okay, so that means there's 5 members of the unit cell. We've got the band structure here. The important thing to notice about the band structure is that the bottom band is Chern number +2. And the next one has Chern number -3. So we got a +2 and we've got a -3 for those 2 lower bands. So that'd be good to remember. +2 and a -3. Now, what happens in this case? We look at the numerics. We see at very low power, we get exactly what we expect. So the lowest band is +2. So when we solve for a soliton low power regime, what happens is the soliton moves over by 2 unit cells exactly through 1 cycle of the pump. You can see that here. So 1 cycle of the pump down here, 2 unit cells over. Whereas something funny happens for intermediate power before you get trapped in this model. You get that the soliton moves over to the left by 1/2 of a unit cell on average per cycle of the pump. So in this case, it takes 2 cycles of the pump to move over by 1 unit cell to the left. Okay, so in other words, fractional quantization. Can't be a Chern number. Chern number's got to be an integer. Moves over by 1/2 a unit cell. So reminiscent of the fractional quantum Hall effect in a way, but obviously not the fractional quantum Hall effect because we're in a mean field bosonic regime here. And then eventually you get self-trapped. So what is going on? First, let me show you the experimental results. So at left is experiment, right is simulation. So now I'm just going to increase the power. Now I'm increasing power. Not much is happening so far, but you're going to start to see the soliton form. And it's forming, it's forming, it's forming. It's localizing. And what you can see is it's moving over to the left as you go downwards. All right, so in the numerics, we see it move over to the left, same as the experiment. And it's moving over to the left by precisely 1 unit cell over 2 cycles of the pump, so fractional motion. All right. So let me try and explain the mechanism that we came up with for this. It's in terms of multi-band 1A function. Okay, so in the integer case, as I explained, you take the 1A function, you see that it moves over by 1 unit cell to the right if the Chern number is +1. But in the fractional case, a little bit higher power means that more than 1 band is getting involved. Okay, so we've got the bottom band is Chern +2, the next band is Chern -3. So it stands to reason that because the power is higher, the matrix elements are stronger, you have that other band participate. So it's reasonable to actually take the multi-band 1A functions corresponding to 2 bands, the 2 lowest bands, right? And so that gives you 2 1A functions. Right? Hold on, let me. So if there's 2 1A functions in a unit cell, what can happen is the following. And we do find 2 solitons, actually, in the numerics. Forgot to mention that. There are 2 different solitons that are kind of braiding, I don't want to say braiding, that are sort of going between one another as a function of energy, as a function, I'm sorry, of the pump parameter in the pump. So there's 2 different nonlinear solutions. Again, reminiscent of the fractional quantum Hall effect in the sense that there are these degenerate ground states that are going between one another. But again, I'm not making the claim that it's equivalent. In fact, we don't know to what extent it's equivalent. Anyway, so here's the yellow 1A function and the blue 1A function. What happens is through one cycle of the pump, yellow goes to where the blue was. And the blue goes to where the yellow was on the next unit cell. And then it takes a full other cycle of the pump for the yellow to come back to where it started on the next unit cell, and the blue to go to the next 1A function where it started. So it's going between these different ground states that are associated with the 1A functions that aren't equal to the 1A functions, but they're associated with them. And that's why you have this fractional behavior. That's why it takes 2 cycles to go through one unit cell. And what we can show is that because of the structure of multiband 1A functions, we have a formula for what these fractions are. So for these 2 bands, it was the sum of the Chern numbers divided by the number of bands. So the sum of the Chern numbers is 2 plus minus 3, that's minus 1, divided by 2 is minus 1. So we get. And there, again, is the experimental results. So we can get, when we go to more complicated models, we can get all sorts of weird fractions. The fractions are always sums of Chern numbers of different bands, divided by the number of bands participating. They're always that, but there are some combinations that we just don't get. And we don't know why. So that's a good question for theorists out there. Why do we get certain combinations, certain fractions, and not other ones? Maybe we just haven't found them. That's very possible. It's possible that you get all combinations, but we have never been able to get them. It also explains this quantization to 0, why we get cell attracting, right, for sufficiently high power. Because the sum of all the Chern numbers are all the bands. And so that tells you, okay, you have really high power, you have a single site, all the bands are participating. The basis number bring the delta function. And so since all the bands are participating, you take the sum of all Chern numbers, that's 0 is 30 minus. That's it. Thank you very much for your attention. Maybe fun.
No, I didn't do that. So I have 2 questions. So the first one is how could you connect the question on all that? And the initial argument about permanence is cool, it's not permanent. Like in any model, you can come up with a bosonic permanent. So what is probably more sort of speaking against it is the fractional quantum Hall state is always driven by energy and not by symmetry. What I mean by that is there is a condensation energy that makes the system adopt this state. So if it were anyway related to fractional quantum Hall state, it should somehow depend on the Soliton density or anything that sort of weaves in an extensive quantity which could relate to an energy. That's I would say that's the thing. For instance, you wouldn't even need a Chern number to create fractional quantum Hall state, just to get to the extreme case. If you design the interactions right, you could even have a fractional quantum Hall effect settling in a band structure that had no Chern numbers. Exactly. So really, like in the theory community, fractional phases are driven by energy, integer phases by symmetry. Now, your initial introduction of the quantum Hall effect brought into another question. So from a different user, to me, your super interesting experiments seem to be as far away from integer quantum Hall effect as they are from fractional quantum Hall effect. Let me explain what I mean. You get a Chern number, that's how far as the similarity goes. Yeah. But then you speak of a quantization because the Chern number is a topological invariant that can only take integers. Yeah. There's many invariants that can only take integers. So if that's already quantization, the key thing in the quantum Hall effect is that you get a one-dimensional quantum wire effectively formed. Yes. And this quantum wire that has a quantized unit response, as you said, in E squared over H.
Yeah.
Probably there's no kind of dissipation that's propagation in your system, right? Probably as you pump the light through this thing, you lose intensity left and right where you get out. That's
Yeah.
right. So my content is that it's super interesting, but the killer thing from our system to one model has always been the dissipation of propagation of these models. And unfortunately, to my knowledge, this hasn't been reproduced in this topological method.
So there's a lot to be, see if I can. So the question is, what quantity is quantized? At least the interface. Let's just forget about interactions, right?
Yeah.
But quantity is quantized is simply the position of one. So if you just look at how it moves, it's true that it's going on. You need something, then measure that's obviously there's a charge, right? So what we can do is look at the way. So if you look at the line function, you just take a center of that, this is the issue, right? Look where it is. Take it center of that. Look at the lower. Look at where it's center of that. That's one. So when that's topological, it's one thing. And in the same sense, there's one thing itself. There is that one. In terms of edge, that's a totally different thing. But for edges, again, there's dissipation. So when you say dissipation list, you say dissipation list because you're not buying things in the electron. It's not, they're not going away, right? They're sticking around, right? In the all that. So the better way to phrase one thing fair comparison between photonics and electronics is backscatter radiation people. So it's in photonics, there's many systems in which it's okay to have a little bit of absorption, loss, you always do. But you don't want backscatter. You don't want feedback. It's a pattern. So there's definitely dissipation, 100%, but there's no backscattering, and the number 6 you have is again on. So it's different.